Welcome to the University of Arizona Global Campus, Future Graduates on Coffee podcast.
Episode 3, Week 3, Database Normalization.
Welcome to the Deep Dive, the shortcut to everything you need to know built just for you. Today, we are taking a necessary detour, really, into the engine room of the digital world. We're talking about the relational database model. This is basically the bedrock structure, the framework that dictates how nearly all modern data is stored and organized.
It really is. And it's not just about knowing what a table looks like. It's understanding the deep mathematical rules and the structural integrity stuff that lets these systems handle massive complexity and do it reliably.
Right.
We're basically drilling down into the principles Dr. E.F. Codd laid out decades ago. And they still govern pretty much every successful database system out there today.
And the sources we looked at have this brilliant way to frame it. They say if older models, the hierarchical, the network ones, were like driving a stick shift.
Yeah, a manual transmission.
Exactly, where the designer constantly had to manage complex physical storage paths. Well, the relational model is the automatic transmission of data management.
That's a perfect analogy, actually.
Yeah.
It frees the designer to focus purely on the logic, what the data means, how different bits of information relate.
Yeah.
You don't get bogged down in how the computer physically stores things on a disk.
Which must have been a nightmare before.
Oh, it was complex. This logical simplicity is really why relational databases, RDBMS, just took over the market.
Okay, so our mission today is to really solidify your grasp on this. We'll define what makes a proper table, understand why keys are absolutely critical, see how data integrity rules kind of police the whole system, and crucially, look at the language, relational algebra, that we use to, talk to the data once it's all set up.
Okay, so the absolute foundation is the relation. Now, conceptually, we usually represent that as a table. Rows and columns, 2 dimensions.
Right, looks like a spreadsheet.
Kind of.
Yeah.
But to talk about it precisely, we really need to use the right terms, ditch the casual ones sometimes.
Okay, I get the need for precision, but why the specific jargon? Why do database people insist on tuple and attribute when, row and column seem perfectly clear to most folks?
Well, it's important because relation itself is a mathematical concept. It's not just a spreadsheet. So technically, a row is a tuple. It represents one single thing, like one specific customer, one product.
One instance of an entity.
Exactly. And a column is an attribute. It defines a specific characteristic of that entity. Using the technical terms, connects that visual table structure directly back to the mathematical rules Codd set up. It keeps things rigorous.
All right. So if a table is aiming for this mathematical purity, what are the strict rules? What characteristics does it have to meet to be a proper relation?
There are a few key ones. First, the order of the rows, the tuples, doesn't matter. Neither does the order of the columns, the attributes. To the system or the user, it's irrelevant. Second, every attribute, every column has to have a distinct name. No repeats. Third, and this is really key for data consistency, the values you store in a column must match that attribute's domain.
Ah, the domain. That's where the database starts acting like a gatekeeper, right? It's the set of permissible values.
Precisely.
So if you've got an attribute for, say, STUGPA, its domain might be strictly defined as numbers between 0 and 4. You physically cannot put a letter Z or the number 5 in there.
Exactly right. And that strict domain definition is absolutely essential for reliable data manipulation later on. You know what kind of data you're dealing with.
And what kinds of data are we usually talking about?
Well, the standard types are things like numeric, obviously for calculations like that, GPA, character data, or strings for text, or maybe identifiers like a phone number you wouldn't do math on.
Right.
Date, which is often stored in a standard format, like Julian, behind the scenes.
Yeah.
And logical, which is just simple true-false flags.
Okay. And all this structure, these rules, they lead us to the absolute core of the table, the primary key, the PK. You said it's a requirement, period.
It is non-negotiable. It's basically the identity card for each tuple, each row. The primary key is the attribute, or sometimes a combination of attributes, that guarantees unique identification for that specific row.
So in a student table, the student ID number, STUNUM, that's a perfect PK candidate.
Perfect. Because it's guaranteed unique by the institution.
Whereas trying to use, the student's last name, stole name, or even first and last name together, that falls apart instantly as soon as you get 2 John Smiths.
Instantly. If that key doesn't guarantee uniqueness for every single tuple, the whole relational model just well, it breaks down. You can't reliably reference anything.
Okay.
So the power of a key, why it works, comes down to this concept called determination.
Determination.
It's simply the idea that if you know the value of one attribute, typically the key, you can then determine the value of another attribute in that same row.
Right, and we see that written formally, like studum, stole name. The student number, the determinant, determines the value of the dependent attribute, the last name. It's a guaranteed one-way street.
Exactly. Now, where it gets a little more technical and where database design purity really comes in is when you have keys made of more than one attribute. We call those composite keys.
Okay.
With composite keys, we have to check for full functional dependence. What that means is the entire set of attributes in the key must be necessary to determine the other attributes. You can't have any hangers on.
Okay, I want to pause on that because this feels like where the design gets really elegant, maybe subtle. If the student number studinum is already unique, why would a designer care if we say accidentally included the last name in the determinant too? Isn't the main goal just uniqueness? Why fuss about minimizing the determinant?
That's a critical distinction.
Yeah.
If you use a key that does contain unnecessary attributes like throwing in the last name with the unique ID number, you've technically created what's called a superkey.
A super key, okay.
A superkey works. It is unique, but it's inefficient. It's structurally impure. Designers care because those unnecessary attributes often lead to wasted storage space, sure, but more importantly, they could introduce problems later, update anomalies, insert anomalies, making the data management much more fragile.
Okay, so the designer's job is really to refine that super key, trim the fat, get it down to the leanest, most elegant version possible.
Exactly. And that minimal key, the super key, stripped of every unnecessary attribute based on that full functional dependence rule, that's called a candidate key.
Candidate key.
These are the eligible options, the candidates, from which the designer ultimately picks the one official primary key, PK, for the table.
Got it. So once that PK is chosen, we then hit the two absolute unbreakable laws of data management, the integrity rules.
That's right. First up is entity integrity. This rule focuses strictly on the primary key. It demands two things. One, all PK values must be unique, which we've already covered. And two, absolutely no attribute that's part of the PK can contain a null value. The PK must always exist, always be defined.
Which brings us right back to the problem of nulls, the absence of a data value. We mentioned they're tricky, but why is a null so bad in a primary key that it's just completely forbidden?
Because if a part of your primary identifier is null, is missing, you've instantly lost that guarantee of unique identification for the row. If you can't uniquely identify the entity basically ceases to function correctly within the system.
Makes sense.
But nulls are problematic elsewhere too, not just in PKs. They create ambiguity. Does null mean the value is unknown? Is it known but missing right now? Or is it just not applicable in this case? You don't know. And that ambiguity really messes with functions like count or average. How do you average values when some are unknown?
Yeah, okay. That's entity integrity. What's the second big law? The one that connects tables.
That's referential integrity, and this one is handled by the foreign key, FK.
Right.
The foreign key is simply the primary key of one table, say the department table's dep code, placed into another table, like the employee table, to establish a link between an employee and their department. The rule for referential integrity is straightforward. Every value entered into that foreign key column must either be a valid value that actually exists in the primary key column of the table it's referencing.
To the real depth code.
Exactly.
Yeah.
Or the foreign key value can be null.
So unlike the primary key, the foreign key can be null. Why the difference?
Well, it depends on the relationship rules. Maybe an employee can be temporarily unassigned to a department. Allowing null here prevents what we call dangling references, having a foreign key value like a depth code of XYZ that doesn't actually correspond to any department in the department table. It maintains consistency across tables. So we've painstakingly built this solid structure with tables and keys and integrity rules. Now, how do we actually query it? How do we get information out?
Right.
That's where relational algebra comes in. It's the theoretical, mathematical way of manipulating the contents of these tables using a set of specific operators. And the whole system works under a property called closure.
Closure. Why is closure so important? What's the big deal that the result of any operation is always another relation, another table?
It's absolutely fundamental for processing. Closure means the output of one relational algebra operation can immediately become the input for the next operation.
Ah, I see.
It lets you chain operations together, nesting them, building incredibly complex multi-step queries, while always guaranteeing that the final result is still a well-defined table structure you can work with. It makes complex queries possible and predictable.
Okay, that makes sense. So let's look at these operators, starting with the unary ones, the ones that work on just a single table. You mentioned select and project.
Right. Select, which is sometimes called restrict, works horizontally. It pulls out a subset of rows that meet a specific condition. For instance, select all students where the stud GPA is greater than 3.5. It gives you back all the columns, but only for those qualifying rows.
Okay, horizontal slice. And project.
Project is the vertical slice. You use project to specify which attributes, which columns you actually want to see in the result.
So combining them.
Exactly. Typically, you select the rows you want based on some criteria, and then you project the columns you need from those rows. That's essentially how a standard SQL select gag, where query works under the hood. Select the columns, restrict the rows.
Got it. Okay, then we have the set operators. These work on two tables, but they have a requirement, right?
They do. The tables involved must be union compatible. That just means they need to have the same number of columns, and the columns and corresponding positions must have compatible data types, compatible domains.
Makes sense. You can't really combine apples and oranges directly. So what are these operators?
Well, they come straight from set theory. You have union, which combines all the rows from two compatible tables, and it automatically gets rid of any duplicate rows.
Okay.
Then intersect, which just gives you only the rows that appear in both tables, the exact duplicates.
The overlap.
Exactly. Difference is like subtraction. It yields all the rows that are in the first table, but are not found in the second table.
Useful for finding exceptions.
Very. And then there's the product CT, or the Cartesian product.
Yeah, the Cartesian product. This one sounds potentially dangerous. If I accidentally ran a product CT on two huge unrelated tables, wouldn't I just crash the server? It yields all possible pairs of rows, right? Like 6 rows times 10,000 rows gives you 60,000 rows.
You are absolutely right. It is computationally terrifying if you do it carelessly on large tables.
So why is generating all that potential chaos even a necessary mathematical step?
Because its purpose is foundational, even if we rarely use it directly in that raw form. Generating every possible pairing, the complete mathematical combination of the two sets of rows, is the raw, unrefined material needed to perform the most critical operation of all, the join.
Okay, here we go. The join. This is where the real power is, isn't it? The intelligent way to combine information from multiple tables that are linked by those common foreign key attributes we talked about.
Absolutely. The workhorse is the natural join. It intelligently matches rows based on the common attributes, usually the PK-FK pair. It merges the data from the matched rows, automatically eliminates the duplicate joining columns so you don't see it twice. And, importantly, it only includes rows that have a match in the other table. Unmatched rows are dropped.
But sometimes you want those unmatched rows, right? Maybe find out which customers have never placed an order.
Exactly. That's where the outer joins come in. A left outer join, for example, returns every single row from the table you list on the left side of the join, even if there's no corresponding match in the right table.
And what happens for the columns from the right table if there's no match?
They get filled in with nulls. This is incredibly useful, as you said, for finding things like customers with no orders, or potential referential integrity problems, or just getting a complete list of entities regardless of their related activity. There's also a right outer join, and sometimes a full outer join. So when we're actually building databases, designing the structure, the relationship designers really strive for is the one-to-many, 1M relationship. That's kind of the ideal architecture.
Like one department has many employees.
Exactly. It's the cleanest, most efficient way to link related data.
And implementing that is straightforward.
It is. You just take the primary key from the one side, like depth code from the department table, and you place it into the table on the many side, the employee table, where it becomes the foreign key. Simple, elegant, controlled redundancy.
Okay, that's the ideal. But what about the trickier one, the many-to-many MN relationship? Like, many students take many classes. You said you can't implement that directly.
You really can't, not without causing massive data redundancy and update anomalies. If you tried to put class information directly in the student table, a student taking 5 classes would need 5 rows, duplicating all their personal info. Or vice versa. It's a mess.
So what's the fix? It sounds like a structural sleight of hand is needed.
It is, essentially. You break the problematic MN relationship down into 2 separate, well-behaved 1M relationships by introducing a third table in the middle.
Ah, a go-between table.
Exactly. We call it a composite entity or sometimes a linking table or bridge table. So for students in classes, you'd create an enroll table.
And what goes in the enroll table?
It would contain, at minimum, the primary key from the student table, say studum, and the primary key from the class table, class code. These two together often form the primary key of the enroll table itself.
Composite primary key.
Often, yes. And maybe other data relevant to that specific enrollment, like the grade received. But the key is, this enroll table now has a 1M relationship back to student. One student can have many enrollments, and another 1M relationship back to class. One class can have many enrollments. The original MN problem is solved. This transformation is absolutely fundamental to good relational design.
Okay. That makes sense. Now, this leads us to something really interesting. We've kind of hammered home the idea that redundancy is bad, it leads to anomalies, avoid it. But the sources give this fascinating, crucial counterexample, the idea of strategic, controlled redundancy. That feels really counterintuitive after everything we've said.
It does, doesn't it? But it's absolutely essential in certain situations, particularly for preserving historical accuracy.
Yeah.
Think about an invoicing system. You have a product table with current product prices, product price. You also have an invoice line table detailing items sold on specific invoices. Why is it absolutely necessary for that invoice line table to copy the product's price from the product table at the time of sale and save it separately, maybe as line price? That's redundant data technically, right?
Yeah, it is. You have the price stored in two places, but I see. If the price in the main product table changes next week.
Exactly.
And you relied only on that main table to calculate the total for an invoice from last month, your historical invoice would suddenly show the new price, not the price the customer actually paid. Your financial records would be wrong.
Precisely. By copying the price into line price at the exact moment of the transaction, you freeze that price, you preserve the exact conditions of that sale forever, you intentionally accept this one specific bit of redundancy, this controlled instance, to guarantee the integrity and accuracy of your historical business records. That's a huge aha moment for many database designers. Not all redundancy is inherently evil.
Wow, okay. That's a really important distinction. So finally, how do designers and the system itself keep track of all these tables, columns, keys, rules, relationships, all this metadata?
There are two main tools we use. For the human designers, there's the data dictionary. Think of it as the designer's blueprint. It provides detailed descriptions of all the tables, the attributes within them, their data types, their domains, maybe constraints or business rules. It's crucial for ensuring consistency, especially when you have multiple people working on the design.
Okay, the human view and the systems view.
That's the system catalog. This is a special database created and maintained by the Database Management System, DBMS, itself. It contains comprehensive metadata about everything the system manages: tables, columns, indexes, views, users, permissions, constraints. The whole works. It's the system's internal record of itself.
And the system catalog must be really useful for avoiding confusion, especially in big projects, like preventing two teams from accidentally using the same name for different things.
Absolutely. Yeah. It helps eliminate database homonyms where the same name is used for different concepts and synonyms where different names are used for the same concept. Both of those can cause chaos in a large-scale design. The catalog provides that central authoritative definition.
Makes sense. And one last quick thing, Speed. We've built this logical structure, but how do we make retrieving data fast, especially from huge tables?
With indexes. Think of the index in the back of a textbook, or maybe the card catalog, if you remember those, in a library.
Right.
An index is basically an orderly arrangement, usually of key values, along with pointers to the actual physical location of the corresponding rows in the table. When you query based on an index column, the DBMS can use the index to jump almost directly to the data it needs. Instead of having to scan through the entire table row by row, it dramatically speeds up data retrieval.
And it's helpful to know, right, that when you define a primary key, the system usually creates a unique index on that key automatically.
Yes. The DBMS knows that primary keys are fundamental for access and joins, so it typically creates that index for you to ensure good performance right out of the box. Hashtag tag outro.
Wow, okay. This has been a real deep dive into the relational model. I think the core takeaway for me is that it's this, well, logical, almost elegant framework built on these two really strict pillars: simple table structures and this rigid enforcement of integrity using keys.
That's it. And it's that purity, that logical foundation, that allows for the kind of flexible, powerful, complex data retrieval that basically powers the modern world, from banking systems to websites to scientific research.
Absolutely. And maybe as you, the listener, continue to explore data, it's worth remembering that this relational model is built on these precise mathematical principles. Dr. Codd even formalized this purity back in 1985 with his famous list of 12 rules defining what a truly relational system should be.
Right, Codd's 12 rules. And our sources clearly point out that even today, most of the big commercial database vendors, well, they don't actually fully support all 12 rules. They make compromises.
Which raises a really interesting final thought for you to consider. If the relational model is supposed to be mathematically pure, what compromises are being made in these real-world databases we use every day? Are they trading some purity for speed, for extra features, for easier use? What are those trade-offs between mathematical elegance, processing speed, and maybe just practical information requirements in the face of massive scale?
Something to ponder. What gets sacrificed and why?
Definitely food for thought as you go on to design or query your own databases. That's all for this deep dive.